Alright guys, I thought I would make a quick video for you because I've had a few questions about the field report for 2200 and I thought I'd just answer some of them here so that you guys can have this as a constant resource to look back on. So the main point of all of the field trips for the first half of 2200 was to teach you guys how to identify facies and start to think about the relationships between those and what that means as far as depositional environment over time and also lateral changes in depositional environment. So what you need to do for the report is you need to take everything that you have learned at each field site, write up a site-specific description of each of those places, what you saw at each site, what the changes were, and what they mean at that specific location, okay? And then you're going to take all of that information that you've written and look at it in the larger scheme of things and do that for all of the sites and talk about how the depositional environment has changed over time and also in lateral distance. So you've got a few different types of sites. You have your anti-dunes, you've got fluvial deposition, and over in the Stockton dunes, you've got sand dunes, okay? So a lot of different types of deposition. And what you're going to do is tell me what that means, essentially. So the whole idea is that you link facies to sea level change, okay? So, for example, how does a fluvial environment react to sea level change? So remembering all of the information that you definitely remember from first year, when we have our river systems, so we've got our mountainous region, then it gets a bit flat, and then it comes down here, and then that's where the sea is. My beautiful diagram here. Okay, the higher elevation, so high elevation equals high velocity. Okay, so high elevation equals high velocity. I'm sorry, my handwriting is atrocious. The closer you get down towards sea level is where you start to have the flatter areas, okay? You start to develop meanders, okay? And meandering rivers are obviously a lot slower than the higher velocity rivers that you have at high elevations, okay? They have time to wander around the floodplain, okay? And so you start to see finer grained material being deposited. So high velocity means that you can move quite large particles, and if you'll remember from the 1050 field trip, I think it was, when we were up at Barrington. Okay, we're in the mountainous areas, well, as mountainous as Australia gets. And if you remember from where we had the fire pit, the majority of the particles in the riverbed were quite large. So it was gravelly, there was the occasional boulder, so quite large material. The further we get away from the source, and also the closer we get to sea level, it starts to slow down. And as the water, in this case, starts to slow down, we can have finer particles be deposited. So if you remember the diagram of your meandering rivers, they look something like this, okay? You have deposition occurring on the inside of the river bend and erosion occurring on the outside. Okay, so your new riverbed, your new river will look something like, it'll be over here somewhere. Like this. Okay, I don't know if you can see that very well. So, because the fastest flowing area is on the outside of the river bend, that's where you have erosion occur, and on the inside of the river bend, you have deposition. And what we see being deposited on the inside of this river bend is sand. Okay, so we have sand particles being deposited there. Further out in the floodplain, which is essentially the entire Hunter region is a floodplain of the Hunter River. What you see when it floods is really fine-grained mud particles being deposited. Okay, so that in itself is a description of the lateral changes that you see in a meandering river. So in the river, you have both erosion and deposition occurring of your larger particles. When you have a flood and that water sits stagnant for a while, you have mud be deposited. Okay, so the finer particles have time to filter out and be deposited. You can also have swamp areas semi-adjacent to your meandering rivers, and those areas could have been billabongs, or so they've been cut off from, sorry, I've got a kitten coming to say hello. They've been cut off from the meandering river, so it's now an oxbow. Can you? Okay, thank you. That's very nice. Or a billabong, as we call them in Australia. And those areas are very low velocity, so essentially they're stagnant, and any material that gets deposited in there is really fine grained, a lot of organic material, and that's how a lot of our coal is deposited. All of our coal, essentially. Okay, so that's when we're starting to slow down in our velocity. Once we reach the sea level, however, something starts to change. So we're obviously still pushing around a lot of sand. And one of the things that hopefully you guys remember is how sand moves on the beach. Okay, so we have it's called longshore drift, in case you don't remember. I have a very stubborn kitten that is definitely trying to get into this video. Thank you. Longshore drift, okay, and that's how the particles, they come in at an angle and then go out perpendicular to the coast, okay, and so they come in at an angle and then go perpendicular to the coast, and they kind of zigzag their way up the coast. And they all, in Australia, on the east coast, end up, the majority of our sand ends up at Fraser Island, which is the largest sand island in the world, and continuing to grow from all of the sand that it's eventually pilfering from further south. Okay, so coastal depositional environments are very different to fluvial depositional environments. Okay, you, instead of seeing a consistent direction or a unidirectional flow, often you see a bidirectional flow, particularly in areas that are influenced by tides. Okay, so this is where it's important with your anti-dunes. So what anti-dunes tell us is, instead of, let me rub out my beautiful drawing that I've done to you. When you think of sand dunes, you think of the typical shape of what you saw at Stockton. Okay, so typical dune shape looks kind of like a wave. It kind of goes like this. Okay, and what that tells us is that it's got a unidirectional flow. Okay, so we have sand particles moving off here or along the top here, and then they fall down and deposit like this, and then they move further and then they deposit like this. And so your sand dunes migrate in the direction of the consistent wind. Okay, so the consistent wind direction. These are unidirectional. What you see at Dudley, is it Dudley? Is something different. So your dunes, instead of having this typical dune shape, are kind of rounded when you look at them in cross section, and instead of forming the typical linear dunes, you see them kind of form these weird little like crescent moon shapes. That's a terrible drawing. Okay, they look something like this, but the top of that is rounded. Okay, so if we have more pointed crests of our dunes in a unidirectional flow, but here we've got a rounded crest, what that tells us is that instead of just being one consistent direction, we also have it going in the opposite direction. Okay, so these are called bidirectional. And we often see them in coastal environments. And hopefully you can think about the types of environments where you would see bidirectional flow in a coastal region. Not necessarily just on beaches, okay? So because the sand is constantly moving on beaches, excuse me, we don't really get much of that material developed or deposited and developed, okay? Areas where the velocity is slow enough that you can have deposition occurring, but also have that bidirectional influence. So start thinking tidal regions, perhaps, where you have an ingoing and an outgoing tide, okay? So that might be an indicator as to why you have bidirectional flow. All right, so as far as what you need to do for your report, you need to, like, tell me, are all of the sites the same? Are they all the same depositional environment? Were they all deposited at the same time? So are they the same age? Do we see the same rock units? Or do we see variations between each site? And what causes those variations? So, for example, in some, like, what causes stratigraphy is a really good question to start thinking about. Like, why do we not just see the same unit consistently in our cliff faces, for example? Susan Gilmore is a really beautiful example of sequence stratigraphy. Okay, so why in our cliff face? Okay, this is my beautiful representation of Susan Gilmore from memory. Why in our cliff face do we see these distinct layers? And what has caused the change? Okay? Why would you go from, say, a mudstone to a sandstone? And then back to a mudstone? And then why would you have coal on top of that? And then a mudstone? And then a sandstone? And then, this isn't accurate to Susan Gilmore, but shush. And then a conglomerate on top of that. So you're going from fine-grained to medium or coarse, back to fine-grained, to super fine-grained and really low velocity. So where we've got coal, can I spell? Where we've got coal, that tells us we've got a swamp environment. Okay, so super low energy. And then we've got mud and then sand and conglomerate again. What the heck is going on? What causes these changes? So thinking about the diagram that I drew before, about how high velocity is high grain size and lower velocity gives us lower grain size, then we can start thinking about how something like this can occur. Okay, so starting with the oldest down the bottom, in this diagram I've drawn that it's a mudstone. So think about the type of environments that you would have a mudstone be deposited. Okay, so there's a few different places. So there's like floodplains, deep ocean, okay, once we get below the wave base, you can start to see mud being deposited. And so that's something to think about there. Sand can be deposited in our rivers. We talked about that before, when we've got meandering rivers. I don't know if you can actually see this text that I'm drawing. And also in our marine environments. So shallow marine environments can have sand. Then we go back to mud. It's like, okay, so we're going either back to a floodplain or back to deep marine. And so you can see here that either rivers, so floodplains and meandering rivers, could explain the sequence from mud to sand and then back to mud again. The thing that throws in the big spanner in the works is this guy, our coal sequence. Now, coal is specific. It is terrestrial, okay? You only have coal being deposited on land. So it is a terrestrial unit that is getting deposited. And that tells us that we have a swamp environment. So that kind of cancels out the opportunity of this being a deep marine mud. And the sand could still possibly be a river or marine environment. The thing that you would then look for there is what type of features you see in that sand unit. If you see all of your beautiful features that you're used to seeing, which might tell you that it's got a unidirectional flow, okay, then you'll be like, oh, okay, this is definitely a riverbed, okay. If it's got bidirectional flow, then we might start thinking about that it's being deposited in a marine environment, okay. So we're sorting out our system. We've got these beautiful features in here, so we're calling it a river. So this won't be deep ocean either. So we've got floodplains, meandering river, floodplains, coal and swamp. Then we've got another mud unit, sand unit, and conglomerate, okay. And so we're going back to floodplains, river, and then conglomerate. Why are we seeing such large grain size being deposited on top? Okay, that's what you need to start thinking about. What the frick frack? We only see conglomerates in real high velocity situations, okay? So large grain size, high grain size, high velocity. So that tells us that this is in a more elevated or mountainous region. Okay? I'm so sorry, my handwriting is atrocious. Alright, so we've looked at our depositional environments for each individual bed, and we've had to do some cross-correlation between those to cross out some options of the depositional environments that you can have. What you now need to think about is why those changes occurred. Why did we go from a floodplain to a river, to a floodplain, to a swamp, to a floodplain, to a river, to a high velocity river? How does that happen? How do those changes occur? And this is something that you really need to start thinking about with sequence stratigraphy, is that this is all occurring in one place, okay? All of this material has been deposited at one site, and we're seeing these changes occurring because of sea level changes, okay? And you need to start thinking about what sea level has to do with the depositional, like the material that's being deposited. So in the first diagram that I drew, where there was the mountainous region and then it came down to a flatter floodplain and then it went off into the marine setting. If we have high elevated areas with high velocity depositing conglomerate, that tells us that in our top layer that we have here must have been in a high elevated area. Okay, it's high elevation, it's moving faster, depositing larger grain size. Which also tells us that when we've got sand being deposited, it had to be at a lower elevation. And the mud and the coal is, again, on a floodplain, so it's a lower elevation, it's closer to sea level. That tells us that between like here and here, as an example, where we've gone from sand to conglomerate, that the elevation has increased. In relation to sea level, okay? So the sea level's fallen. And you can see variations throughout that in your sequence stratigraphy. So when you go from a sand to a conglomerate, you have a rise in elevation, which tells us that there's been either global or regional sea level fall. Okay, those two are distinctly different. When you have global sea level change, it's due to obviously things that are causing global changes. So freezing or melting of polar ice caps, for an example, will cause global sea level change. Regional sea level change is usually the direct result of tectonic stresses. So when you have folding or thrusting due to compressional sequences, and that particular area that you're in has been uplifted in relation to sea level and as well as in relation to the surrounding area, then you'll have regional changes. And so you might find that one particular site looks like it has had regional changes that haven't affected a site 100 kilometers up the coast, okay? And that's all region specific. And so what you need to do with all of your information, now that you know everything about sequence stratigraphy and you know everything about your sites and how and why you think that those changes occurred, you need to give me a description of all of the field trips as a whole. So be like, at this site, we discovered blah, blah, blah. At this site, we discovered X, Y, Z. And I want you to tell me the lateral relationships between those sites, whether you see similar features in site A that you do in site B. So kind of like how you did at Dudley, where you had to do the lateral variances in the coal seams where they pinched out and where they reappeared and things like that. That's telling us the changes in that site-specific area, so within like 15, 20 meters. What I want you to do is look at the bigger picture and tell me how things change between each site, okay? And what that means for the depositional environment for each site, and what that means overall. So are all of the sites the same? What causes the variations between those sites, not just in your beds, but also specifically for each site? And what does it mean when you have repetition in your sequence? So when you go from mud to sand to mud, what does that mean? Why is that happening? Why is that occurring? Yeah, I think that hopefully this little summary that I was hoping that would be significantly shorter than it is, will help you out a little bit as far as your report is concerned. So we don't want 3 or 4 different like individual reports. I don't want you to give me a site report for each location that you went to. What I want you to be thinking about is the bigger picture. So you've got your individual sites that you went to, you have that information, and what I need you to do is tell me why we see changes between those sites. Okay? Why is there variation? What is going on? Put them in age order, tell me about the depositional sequence that you see in that time period, and then link all of the changes that you see to something like sea level changes, and how they have all reacted to regional and global sea level change. Okay, I think that's about it. If I've got paper everywhere here. If you have any questions, feel free to email me. I am available. If you guys want to catch up as a group, maybe you can sort out a time that works for you guys. I charge $40 an hour, so if all of you turn up, it's like $5 each or something like that. Or if you want to catch up one-on-one, just email me and let me know. But hopefully this has provided a little bit more clarity. I hope I haven't confused you even more. Yeah, let me know. My email address, I'll put it in the links for you. And I hope you guys are having a fantastic day. I hope this helps. I hope you can go away from this with feeling much calmer and ready to write your super amazing reports that I look forward to reading. And yeah, I'll hear from you guys soon.